Okay, our next speaker is Krejcik from SLAC, who will be presenting Diagnostics and Instrumentation and Challenges at LCLS-II. Patrick is the head of the Diagnostics Development Department in the SLAC Accelerator Directorate, responsible for advanced diagnostic systems for the LINAC Coherent Light Source Accelerator and the new LCLS-II project currently under construction. Patrick has participated in numerous accelerator projects over 27 years at SLAC, and before that worked in both CERN and Germany on international accelerator projects. Patrick originally received his PhD in physics in Sydney, Australia.
Good morning. Thank you for this opportunity to talk about some of the challenges facing our new LCLS-II project. LCLS-II is an extension of the LINAC Coherent Light Source, which has now been operating successfully for a number of years. It uses the existing 3-kilometer tunnel of the 60-year-old LINAC at SLAC, and it uses the last 1/3 of that tunnel. Our new project is going to remove the first kilometer of that original LINAC, in fact that's already been done, and replace it with a new superconducting LINAC to provide CW beams for LCLS-II. There's a new very large cryo plant. I think it will become the world's largest refrigerator to keep that 1 kilometer of LINAC cold. Then there are some bypass lines to transport that CW beam to the end of the 3-kilometer tunnel to where the undulators are to produce X-ray photons. And there'll be 2 new undulators, one for soft X-rays, one for hard X-rays. So we will use all the existing experimental stations from LCLS-I. It's a collaboration between all the national accelerator laboratories in the United States, and we expect to see first light in 2020. We begin a 1-year shutdown at the end of next year for the installation, first light then in 2020. So what are some of the accelerator challenges that we face for this machine? So in X-ray FEL, it's characterized by the need for high brightness beams with very high peak currents in very short bunches, peak currents of the order of kiloamperes, and brightnesses with emittances of the order of 1 micron. So our diagnostic systems therefore have to require measurements of very small transverse beam sizes. And in the longitudinal phase space, we have to measure ultra-short bunch length measurements of the order of femtoseconds. Bear in mind that this is also a single pass machine. So a single pass machine requires bunch by bunch measurement, unlike a circular machine where the same bunches keep going round and round. So if that were not challenging enough, we now have new requirements for our superconducting LINAC, where we have very high average beam power, 250 kilowatts of average beam power, which can melt anything in its path. And so the diagnostics have to be minimally invasive in order to survive. The high repetition rate of 1 megahertz of the bunches now also implies very high data acquisition rates. So those 2 things means that the diagnostics and the controls instrumentation have to be fully integrated both with the timing system and the machine protection system. And as I said, I'll be talking mainly about the accelerator challenges. On Monday, Dan Flath talked about the photon control system. So this is the accelerator side of the talk. So what are the differences between the 2 systems? We have at the top here the cartoon of the layout with the superconducting LINAC here, the bypass line, and then the existing warm S-band LINAC here, and transport lines going to 2 undulators. So whereas LCLS-I was a warm, normal conducting S-band pulsed LINAC, LCLS-II now operates at a lower frequency, 1300 megahertz RF, but it operates CW, so continuous operation. The repetition rate of the original LINAC was 120 hertz, so a pulsed machine where the power from the klystron was pulsed. Now this is upped from 120 hertz to 1 megahertz. LCLS-I had an energy range from 3.5 to 14 GeV, so it could do both soft and hard X-rays. The new one will initially be limited to 4.5 GeV, so mainly soft X-rays, but a future upgrade to hard X-rays as well. And then, as I mentioned, 250 kilowatts there of average beam power. So this is just a shopping list of all the diagnostics that you have to put on an accelerator. Time doesn't permit going through all of them, of course. So I'm just going to highlight some of the main differences. So we have 120 hertz in the existing system. Now we have a megahertz data acquisition rate. In our existing system, we have buffered single bunch beam synchronous acquisition from all devices on all consecutive bunches. So it's a single pass machine. You have to be able to measure the same bunch on all BPMs, all bunch length measurements at the same time. We still have that requirement in LCLS-II, but we have to do it now at a megahertz. So that's a control system challenge. The control system is EPICS based in both machines. It was implemented with VME crates and discrete processor boards in LCLS-I. We have now developed a new common platform for the high performance systems in LCLS-II based on ATCA crates and board level FPGA processing in order to attain the necessary processing speed. In LCLS-I, the timing system was an event-based system which was distributed with discrete timing receivers. In LCLS-II, in order to cope with the high rate, we now have a pattern-based timing system, and the timing receivers are now embedded into these common platform processors. The machine protection system in LCLS-I operated over a dedicated network, and it had to have a bunch response time of 8.3 milliseconds. That was the time between LCLS-I bunches. Now on LCLS-II, the machine protection network has to have a response time of 100 microseconds. So quickly now, the status of the common platform. The hardware has been completed. The firmware is in place, the firmware being used for subsystem development. All the timing system and MPS-based firmware is integrated into this system, and we're at the stage now where we're doing the procurement, and production is underway for what we call the early injector commissioning, which will start next year already. This is a sort of schematic of the common platform architecture. A complicated diagram, but what I wanted to point out here was that the application firmware on these board level processors is specific to the application. So you'll have firmware for the low level RF, firmware for the BPM processors, and so on. But common to all of these is the timing system, the embedded timing system, and the MPS machine protection system interface. So the LCLS-II timing system is a distributed timing system as it is in LCLS-I. It's the accelerator system over 3 kilometers has a long haul phase reference line for the low level RF and a separate timing distribution over fiber network system. So in the 1 megahertz machine, you need a lot of flexibility in the timing pattern control so that you can do arbitrary bunch trains from 1 hertz to 1 megahertz. And as I said, beam synchronous acquisition as well. Timing pattern has some new features. The pattern that we broadcast contains something we call metadata. This is an innovation where we have within the timing pattern something like the requested bunch charge. The reason for doing this is that in the, well, let me get to that in the next slide, but this is a quick status of the timing system here, developed and integrated into that common platform. The machine protection system has to deal with this 250 kilowatts of beam power. You can shut the beam off either at the gun or at the fast kicker here. The inputs to the machine protection system are distributed along the kilometers of LINAC and go to a common processor, and we try and achieve less than 100 microseconds to shut that off. The various devices distributed along the machine are in these modules here, which can accept arbitrary inputs from beam loss monitors and other devices, and they go to a central node where there is logic processor. So going back to this slide here where I mentioned the innovation where we would have metadata in the timing system, if we tell the bunch that it's going to be, for example, 100 picocoulombs on that bunch, a beam position monitor can then compare that measured charge with the requested charge, and if it sees a difference, immediately abort the beam. We find this to be simpler and more reliable than, say, comparing two measurements within the machine and having noise issues to determine whether the beam exceeds a certain threshold of loss. So finally, I'm going to select just two examples of the diagnostic challenges that we face. I pick one from the transverse beam size measurement and one from the longitudinal bunch measurement. Profile monitor screens don't tolerate high repetition rate. They're also susceptible to coherent radiation from microbunching instabilities, so we rely on fast wire scanners to do our beam size measurement. And for the longitudinal measurement, we rely on RF transverse deflecting cavities to streak the beam in order to obtain sub-femtosecond resolution. So a quick picture here of the fast wire scanner developed at LCLS-I, which will be used in LCLS-II. It's a linear DC servo motor acting through dual bellows here, and at 45 degrees to the beam, so you can measure in 3 planes, X, Y, and U. And in order not to destroy the wire, it has to move at speeds of almost a half a meter per second in a controlled way. We also found that as the machine repetition rate changes, you have to be able to slow that wire down to both protect the wire and acquire the data. So we have some complex motion control requirements here. This is the position of the wire shown on this line, and these are the beam signals here. So we slow down for slow repetition rates to acquire the beam data, then speed up to the next wire, slow down again. Some lessons learned. This complex trajectory and speed control is required. We have position encoders that are read back synchronously with the beam, but we also need to monitor the motor current. The PID servo loop can go unstable in regard to the motor current, as shown in this black trace here during this complex motion control. So it's not enough just to record the position of the wire, but also record the current in real time from the motor. Finally, the transverse cavities are now a well-established longitudinal diagnostic. You have an off-axis screen. When the bunch goes through, it's streaked, and the length of that streak on the screen is a measure of the bunch length. We've now upgraded that to operate at X-band in order to get the high resolution required for LCLS. This is a picture of it installed in the undulated beamline. Because it's located after the undulator, it's non-invasive to photon user operation, so we can operate it on every single bunch of the beam, and we look at the profile monitor screen after the vertical beam dump there. It's a most versatile diagnostic, but it's also, it might be regarded as a 5-star diagnostic, but it also comes at a 5-star price, so it's not in everyone's budget, but it does pay for itself in the long run. It uses every aspect of accelerator control systems. It uses low-level RF, obviously, timing, imaging, machine protection, etc. But since it's downstream of the undulator, it's the only single-shot diagnostic that we have that can reconstruct not only the electron bunch profile, but also the photon bunch profile. And that has allowed us to do a number of exotic pump probe setups for users. I have a little quick animation here of the screen as we put in a slotted foil. This is kind of nice demonstration of the capability. You'll see as we go to 2 slots here that you can now see 2 X-ray pulses here. There's the 50 femtosecond timescale, and as you vary the slot separation, you can vary the relative timing of two photon bunches. So that allows for some exotic experiments at LCLS. So there are many new challenges with ultra-fast attosecond bunches we have at SLAC. If you'd like to consider joining us to meet some of these challenges, we have a number of openings now available for electronics, controls, software, and engineering. If you're curious, check out our website at SLAC. Thank you.